There is something that happens when you look at the night sky that doesn't happen when you look at anything else. It's not just aesthetic. It's not just that the stars are beautiful or that space seems vast. There is something that changes in your nervous system, in your perception of time, in the activity of certain regions of your brain that instruments can measure and that researchers have begun to document with precision over the last 20 years. And there is something else, something that physics adds to what neuroscience already knows. Every point of light you see in the night sky is not a picture of what that star is like right now. It is information that traveled through space for years, centuries, or millennia before reaching your retina. When you look at a star 400 light years away, the photons hitting your rods and cones right now left that star 400 years ago. What you are processing in this moment is not the present of the cosmos. It is its past arriving to you in real time. Your brain, that information processing machine built by millions of years of evolution to handle the immediate environment, was never designed for this kind of input. It evolved to process distances of meters, threats seconds away, social relationships in groups of a few dozen individuals, not to process light years, not to integrate the information that the point of light you are seeing right now is radiation emitted by an object at a temperature of thousands of degrees at a time before your birth, possibly before the birth of your grandparents. When that happens, when the scale of the cosmos enters through the eyes and the brain tries to process it, something in the cognitive architecture doesn't fit. And that mismatch has specific physiological consequences that researchers can measure. What psychologists Dasha Keltner and Jonathan Haidt of the University of California, Berkeley described in an influential article published in the journal Cognition and Emotion in 2003 as awe, astonishment, or reverence, has a neurological and physiological signature that distinguishes this experience from other aesthetic or emotional experiences. But before getting into the mechanisms, there is a question Penrose would consider the most important of the ones we can ask here. Why does the scale of the cosmos affect the brain in a way that the scale of a tall building, or a mountain, or even an ocean does not exactly produce? What is it about the astronomical scale that makes it qualitatively distinct from any other experience of vastness the human brain can have? The answer to that question demands precision about what the astronomical scale really entails for the brain. When the visual system detects a star, it registers direction, apparent brightness, and color. Those three data points are all the eye can capture: the actual distance, physical size, surface temperature, age of the star, photon travel time. None of those data are in the sensory stimulus. They are in the cognitive map the brain constructs from prior knowledge about what those signals mean. And here lies the key to the experience we are interested in. When the brain has that knowledge, when it knows that the apparent brightness of Sirius, the brightest star in the night sky, corresponds to an object 8.6 light years away with an intrinsic luminosity approximately 25 times greater than that of the sun, the experience of looking at Sirius changes qualitatively. The point of light ceases to be just a point of light. It becomes a specific physical object with known properties at a distance the brain cannot process intuitively but can represent conceptually. And that combination of direct sensory perception with conceptual representation of a scale exceeding all everyday experience is exactly what activates the mechanisms of awe more intensely than any other experience of vastness the brain can have. The answer has to do with something no other source of vastness produces: the combination of spatial scale with temporal scale. A mountain is large, A star is large and it is in the past. And that combination, that of simultaneously processing a distance exceeding all everyday experience and a time interval exceeding the duration of a human life, activates the brain in a way that has no equivalent in any other object of ordinary experience. It was looking for answers to this that I found this digital book. The Penrose Dossier, What Academia Fears to Admit, is not a book about astronomy or neuroscience. It is a tool for developing the disposition that makes it possible to hold the real scale of the cosmos without immediately reducing it to something more manageable. Penrose has a capacity few scientists cultivate deliberately, that of letting the magnitude of a problem remain in all its magnitude, without rushing to tame it with analogies or manageable numbers. This book documents that stance with precision. Not the result, the habit of thought. You are in the precise state where this matters. The mind still open, the previous model still not closed. It is not a state that lasts long. Take advantage of it now. The link is in the first pinned comment, but beware. This content may be taken down. Click now. Download your copy. When was the last time you looked at the night sky with real attention, with no concrete destination for your gaze? What happened inside you at that moment? Leave your answer in the comments. To understand what happens in the brain when it processes the astronomical scale, one must first understand how the brain processes scale in general. The human visual system has distance estimation mechanisms that work with remarkable precision up to a few hundred meters, using binocular disparity, motion parallax, perspective, and relative size of familiar objects. Beyond that distance, the visual system relies almost exclusively on monocular cues dependent on prior knowledge about object size. And beyond a certain threshold, the system simply lacks the sensory information necessary to calculate real distances. The sun and the moon appear the same size, even though their distances and diameters are radically different, precisely because the visual system has no direct access to their true distances. The moon illusion on the horizon, appearing larger than when at the zenith even though its angular size is identical, is a well-known example of how the brain uses context and depth cues to estimate size, and how that process can produce perceptions that do not correspond to the physical reality of the stimulus. The perceptual system was optimized for the evolutionary environment, not for astronomy. When you look at a star, the visual system registers a point of light with a certain intensity. It does not register distance. It does not register real size. It does not register photon travel time. That information is not in the sensory stimulus. It is in the knowledge the brain has of what a star is, of what a distance of light years means, of what it implies for the light to have taken that long to arrive. And processing that conceptual information simultaneously with the sensory stimulus produces something awe researchers have consistently identified: the need for cognitive accommodation. The term Keltner and Haidt, used to describe the process by which the brain attempts to integrate an experience that exceeds its existing schemas. That accommodation process is not metaphorical. It has measurable physiological correlates. Brain imaging studies conducted by Keltner's team at UC Berkeley, published in the journal Psychological Science, show that experiences of awe are associated with activation patterns including the medial prefrontal cortex, regions of the limbic system, and, notably, a relative deactivation of default mode network areas processing the narrative of the self. When the brain is in awe mode, it is less busy generating the continuous story of who you are, what you need, what you have to do next. That self-narration, which in ordinary conditions consumes a significant fraction of attentional resources, is partially interrupted. The physiological result of that interruption includes changes in the autonomic nervous system consistent across studies. Sympathetic activation associated with stress and the fight or flight response decreases. Parasympathetic activation associated with rest and recovery increases. Heart rate tends to drop slightly. Cortisol levels, the stress hormone, show measurable reductions in studies using awe induction protocols of 5 to 15 minutes. The brain literally slows down. There is one aspect of the physiology of awe especially relevant to the argument Penrose would make here. The studies from Keltner's Berkeley team mentioned are not the only ones documenting the physiological effects of awe before vastness. Research published in the journal Emotion in 2015 by Yang Bai and colleagues at UC Berkeley found that awe produces a consistent reduction in immune system inflammatory markers, measured via pro-inflammatory cytokines in saliva samples. Participants reporting awe experiences showed lower levels of interleukin-6, an inflammatory marker associated with the chronic stress response. That means the experience of awe before vastness not only produces transient effects on mood or time perception, it produces measurable effects on the immune system, presumably through reduced activation of the hypothalamic pituitary adrenal axis, the stress response system. Contemplating the cosmos has a biological correlate going beyond subjective experience. It is a physiological process with immune system consequences that instruments can detect. Penrose would not present this as the central argument, but would note there is something remarkable about the fact that exposure to the real scale of the universe produces physiological effects opposite to chronic stress. The universe, in that sense, is not just the object of study of physics. It is part of the environment to which the human organism responds with mechanisms evolved before anyone understood what a star was. The link is in the first pinned comment. The last units are running out. Click now and start your journey toward the clarity and genius you deserve. But there is a dimension to this experience neuroscience alone cannot fully capture, requiring the physical layer Penrose would bring to this conversation. Because the awe produced by looking at the night sky is not simply the awe produced by any vast stimulus, it is the awe of processing real information about the past of the universe. Every star you can see with the naked eye is at a distance ranging from just over 4 light years for Proxima Centauri to several thousand light years for bright stars like Deneb. In the constellation Cygnus, whose exact distance is hard to determine precisely, but which astronomical catalogs estimate between 1 and 2,000 light years. The photon arriving at your retina from Deneb left that star sometime between the year 1000 and 1200 CE. During the European Middle Ages, probably around the time of the First or Second Crusade. That is not a pedagogical metaphor, it is physics. The speed of light is a constant known with extraordinary precision, exactly 299,792,458 meters per second in a vacuum. That speed, combined with the distance to the star, dictates exactly how long the photon took to arrive. And that photon is now part of your visual experience, being processed by your visual cortex, triggering cascades of neural signals in your brain right now. Penrose would point out there is something in that situation having no equivalent in any other ordinary human experience. In any other interaction with the environment, the information you receive through your senses comes from the present or the immediate past, fractions of a second ago. The speed of sound, much slower than light, introduces delays of milliseconds to seconds for distant sources, but even those delays are perceptually negligible in most everyday contexts. When looking at a star, the delay is not milliseconds. It is years, centuries, or millennia. You are receiving information from a state of the universe that existed before you existed, possibly before any human being existed. That information does not arrive labeled as ancient. It arrives as direct sensory experience, as light hitting your retina right now. Processing the temporal distance is an extra step requiring explicit knowledge, not direct perception. And the coexistence of that conceptual information about the photon's antiquity with the sensory immediacy of receiving it now is one reason the experience of looking at the night sky with astronomical understanding is qualitatively different from looking at it without that knowledge. There is a study relevant to this point deserving precise mention. Researchers at Stanford University, in a paper published in Psychological Science in 2012, found that awe experiences produce a specific alteration in time perception. Participants who had experienced awe consistently reported having more time available than control group participants, even though the actual amount of time was identical. That effect on time perception, which the authors termed time expansion, is one of the most replicated findings in awe research. The proposed interpretation is that the awe experience interrupts processing of the self's temporal narrative. The continuous sequence of recent, past, and future anticipation that normally occupies a significant portion of attentional resources. When that narrative is interrupted, the present expands subjectively. Time feels more available because the brain stops consuming resources, projecting into the immediate future, and ruminating on the recent past. The link is in the first pinned comment. The last units are running out. Click now and start your journey toward the clarity and genius you deserve. Penrose would take this point in a direction awe psychologists generally do not go. That expansion of the present produced by contemplating the sky is not just a subjective perceptual effect. It is, in a way, an approximation of the physical reality of time described by relativity. Time does not flow at a uniform rate. There is no point-like present moving inexorably toward the future. The ordinary experience of time as a continuous stream is a brain construct, a useful narrative for survival, not an exact description of the structure of time. When that narrative is interrupted, when the brain stops generating the continuous flow of me now next and falls into something closer to an expanded experience of the present, it is not making a perceptual error. It is, in a way, approaching the real geometry of time, a dimension where all moments coexist, where the present is not especially privileged over any other moment, where the cosmos's past arriving as stellar photons is as real and present as the observer's here and now. This is not mysticism. It is the consequence of what happens when the brain tries to process a scale of information it was not evolved to handle. The human brain evolved in the Pleistocene, in small groups, managing distances of tens of kilometers and time horizons of decades. When that brain receives information about an event occurring 1,000 years ago, thousands of light years away, normal time processing mechanisms simply lack an adequate schema. And in the absence of an adequate schema, the self-narrative system, which normally dominates subjective experience, is partially suspended. The Milky Way, visible from low-light pollution latitudes as a faint band of light across the sky, is the projection onto the celestial sphere of our galaxy's disk, seen from within. The Sun is located approximately 27,000 light-years from the galactic center, in an outer spiral arm called the Orion Arm. What we see as that diffuse band are the hundreds of billions of stars lying in the disk plane, too distant to be resolved individually by the naked eye, but numerous enough to produce a detectable diffuse glow. Penrose would point out that seeing that structure and understanding it is a 100,000 light-year diameter disk we are part of activates spatial intuition in a way no diagram in a book can fully replicate. The difference between reading about galaxy structure and seeing its projection in the night sky is the difference between knowing a geometry's properties and inhabiting it. Throughout his career, Penrose developed visual tools, diagrams, and spatial representations because he believed the geometry of the cosmos has a reality exceeding algebraic notations. Equations are maps. The territory is the real structure, and the night sky is the territory, available to any observer anywhere on the planet looking up knowing what they are seeing. Now, I need to speak to you directly, because there is something in all this having immediate consequences for anyone living under a visible sky, which includes, to some degree, almost everyone almost everywhere on the planet. The brain you are using right now is the exact same brain that, if exposed for 60 seconds to the experience of looking at the sky with real attention, with the knowledge of what you are seeing, will undergo measurable physiological changes. Sympathetic activation will decrease. Heart rate will drop slightly. The narrative of the self will be partially interrupted, and the perception of available time will expand. 60 seconds. Not an hour of meditation. Not a spiritual retreat. 60 seconds of looking up, understanding each point of light is a real physical object, sending information from the past. The reason Penrose would find this significant is not therapeutic. It is epistemological. Contemplating the cosmos with physical understanding does not just produce physiological effects, it produces access to a scale of reality the brain does not ordinarily process. And processing that scale, however briefly, however imperfectly, changes something in the cognitive architecture the brain uses to approach everything else. Mathematicians and physicists describing the experience of having an insight into space-time geometry, from Einstein to Penrose, have consistently noted that understanding has a visual, spatial, almost physical component, not just symbolic. The geometry of the cosmos is not just a set of equations. It is a structure that can be intuited, even if partially, by a brain exposed to the real dimension of what those equations describe. Looking at the sky is a way of calibrating the brain to the real scale of the universe, not completely or definitively, but in a real physiologically measurable way. And that scale adjustment, that interruption of the habitual self-narrative, that brief contact with information from the cosmos's past, produces a brain that processes things slightly differently for the next few minutes. Slower in a good way. More capable of holding an unresolved idea. Less urgently oriented toward the next practical step. More receptive to the kind of thinking producing the insights science needs and ordinary stress makes impossible. There is one last consideration to make explicit because it connects everything we have seen with how Penrose inhabits physics. Throughout his career, Penrose has developed visual tools, diagrams, geometries, spatial representations, allowing him to think about physics problems in ways ordinary algebraic notations do not facilitate. Penrose diagrams for quantum processes, Penrose-Carter diagrams for the causal structure of space-time near black holes, Penrose tilings in quasi-crystalline geometry, all are examples of a way of thinking prioritizing visual and spatial structure over purely symbolic manipulation. This predilection is not an accident of style. Penrose believes, and has argued in different contexts, That the geometry of the cosmos has a reality exceeding the mathematical representations we use to describe it. The equations are maps. The territory is the real structure of space-time curved by mass, of photons traveling through vacuum, of singularities where curvature becomes infinite. And the brain exposed to that structure even incompletely and mediated by photons traveling for centuries has access to something the brain reading only equations does not: the direct vertigo of its real dimension. That vertigo is not a mystical experience. It is information. It is the brain receiving input on a scale of reality for which it lacks adequate evolutionary schemas, and responding to that inadequacy with exactly the mechanisms research documents: suspension of the self-narrative, expansion of the subjective present, reduction of chronic stress, cognitive openness facilitating the nonlinear thinking from which insights emerge. So keep this concrete image in mind. Tonight, if you have access to a sky where a few stars are visible, stop for 60 seconds. Not as a spiritual exercise, as a physical experiment. Look up and remember each point of light is a photon that traveled years or centuries before reaching your retina right at this moment. That you are receiving information from the universe's past through your visual system right now. That the brain processing that information will respond to that scale with physiological changes instruments can measure. Penrose spent decades looking at the cosmos's structures through equations. He found there a geometry he found genuinely beautiful, not as a metaphor, but as a real structure. And he repeatedly pointed out that this geometry of space-time curved by mass, of photons traveling the vacuum for millennia, of singularities where time loses ordinary meaning, is available to anyone who looks up and knows even approximately what they are seeing. The cosmos is not far away. It is hitting your eyes right now in the form of photons traveling longer than you have been alive. What changes when you know this is not the sky? It is you.